Hi. April 1st for most people is considered April Fool's Day, but in 1867, April 1st was really Genius Day, and society has benefited immensely from it. I'll tell you more about it later. Until then, Intermolecular Forces of Attraction, huge title, really needs that monster truck announcer guy. We're going to short form it in writing to IMFA, but it's actually easier to say intermolecular forces. So you'll be hearing that a lot. What in the world is an intermolecular force of attraction? It's a force of attraction between two separate molecules, and I really want to emphasize between and separate. It can be the same type of molecule or different types of molecules. So I can be talking about two molecules of water, or I can be talking about, say, a sugar molecule and a water molecule. And when we say intermolecular force, it's the inter part that's kind of important. Because we can also have forces of attraction that hold the molecules together. And that really comes down to when the nucleus of one atom attracts the electrons of another atom and vice versa. So that mutual attraction. Those, if you want to get a term for it, are intramolecular forces. We're not going to use that term, so you don't have to worry about keeping them straight. But if you think about when we have intramural sports, it's inside of school. And when we have intervarsity sports, it's between separate schools. So that we do have those prefixes being used in other ways for the same type of between and within. So let's take a look at two molecules, two separate molecules. I will need to be talking about intermolecular forces, so between two molecules. So if I'm looking at, say, the carbon and hydrogen up here, no, that's not going to be an intermolecular force. If I'm talking about the carbon and oxygen here, no, that can't be an intermolecular force either. But if I'm talking about this hydrogen on one molecule to the oxygen on the other molecule, now I can be talking about a force of attraction between two molecules. Now I can be talking about an intermolecular force. As a comparison, because I still have to keep the bonds straight, and now I'm talking about intermolecular forces. So the intermolecular force is always going to be a very weak force in comparison to the covalent bond. So we won't get into inter and intra, but I still need to remember that the covalent bonds are there and they're very strong in comparison to, but these intermolecular forces can now start to play a role in the more bulk properties. So when I'm talking about chemicals, when I'm talking about molecules, I can kind of focus on just one molecule, but the reality is when I'm talking about samples of things, I usually have hundreds, thousands, millions of these molecules, and they can interact with one another. Then I need to be talking about intermolecular forces. Every single particle can experience these intermolecular forces of attraction. They're there. However, not only do they determine things like boiling points, solubilities, and there's that crazy word, etc., which means it's going to get bigger, but sometimes they're very weak forces and sometimes they're stronger forces. Now, it's important to realize that when I say quite strong, they're still much, much weaker than a bond. Okay, so let's start with this, states of matter. You know, you've seen diagrams like this lots of times. I can think of this as being, let's say we'll start out with water. So I have water. Now water in its solid form we call ice. And in that solid form the particles are held in position, so an ice cube keeps its shape until you melt it, I guess. But it keeps its shape because the particles are held in position. Intermolecular forces. This water molecule holds onto that water molecule, which holds onto that molecule, not bonded, just holding on to. Then I can take that water, that ice, and I can heat it up. I can add energy to it. Now when I add energy to it, the molecules start to move around, and eventually they start to move away from each other. Now as they move away from each other, the thing melts. And you see in my liquid here, I've got some particles that are kind of close together and some particles that are kind of far apart. But as they're moving around, they're going to be, as they get closer, maybe attracting and then pull away again, maybe attracting over here to a different set, and so on. And then I can keep heating it up and I can eventually get to a gas where you'll notice that all the particles are very far away from each other. and there's no interaction whatsoever. The other thing I can do is I can look at this as one temperature. So let's say I've got 20 degrees Celsius. Well, at 20 degrees Celsius, I can have some substances that are a solid. Let's say, for example, sugar. I can have some substances that are a liquid. Let's go back to our water. And I can have some substances that are a gas. So let's say carbon dioxide. And what that means is that at one temperature, and temperature is connected to energy, sometimes the particles are held tight, stronger intermolecular forces. Sometimes the particles are held medium intermolecular forces. And sometimes the particles are held not at all, very weak intermolecular forces. Now it's important to realize that as we go through the different types of intermolecular forces, I'm not automatically referring to sugar, water, and carbon dioxide gas. Let's start with London forces. London forces is going to take us a little bit longer because they are kind of a complicated thing. But all atoms are capable of London forces. They are the weakest of the intermolecular forces of attraction. Now when I say all atoms, all molecules as well. If we have other forces, because these ones are so weak, if there's other forces, other stronger forces, then we can just focus on the dominant, the stronger of the forces available, and ignore the London forces, the weakest ones. But sometimes that's all you have available to you. Now, we've not finished our discussion of nonpolar and polar molecules, but we already know about a nonpolar bond and a polar bond. So let's think about a nonpolar bond for a minute. In a nonpolar bond, we had equal electronegativity, so there was no partial negative, partial positive charge on that. So we had equal sharing. So if that extended into a molecule, now we're talking about a nonpolar molecule. Well, if it's a nonpolar molecule and we don't have distinct ends, we don't have partial positive, partial negative, how do we get this intermolecular force? London forces are the result of an instantaneous dipole. And dipole, of course, means your two ends formed as electrons are moving. Let's get a picture of that. If I have a helium atom here, if I have this atom of helium and I've got these electrons orbiting the nucleus, well, there's no charges there at all. But if you think about it for a moment, this negative pair of electrons right now is here and not over here. So when they're not over here, then if I were to look at this molecule right now, this top side has a negative charge. The bottom side only has the positive charge. So I have this instantaneous positive negative forming. Of course, it's not going to last for very long, but for an instant, when I have the negative charges over here, there will be a slight attractive force between the positive half of one helium atom and the negative piece on the other. Likewise, this helium atom over here, there will be this very weak, very short-lived electrostatic force of attraction, intermolecular force of attraction between those two atoms. If I extend that, now I'm looking at hydrogen molecules. Same thing happening. So right here, this pair of electrons is orbiting, they're being shared. So at one point they're being shared in between, at one point they're being shared exclusively on one atom, and then as they orbit around, they'll move over to the other atom. So right now I've got this all by itself nucleus, I've got this pair of electrons over here. There'll be that very brief, very weak electrostatic charge develop, and then that gives me the opportunity for opposite charges attracting. Dipole forces. Dipole, as we know, means two ends. So what I have is two ends and two more ends. So if we think about that, it's formed between two polar compounds. So the partial charges, those are the poles, they're larger than what we would have in a nonpolar, of course, and they're also longer lasting, so they're a little bit more permanent. So if I take this shape as my polar molecule, where I've got a partial positive charge on one side, partial negative charge on the other side, and I do mean partial, we're not talking about ions here, but partial charges on either end, and I bring a couple others nearby. Well, you can see that I've got a dipole here, and I have a dipole there. Two poles in one, two poles in the other. And actually, I have a third dipole here. But we're going to focus on two at a time. So I have the possibility of an attractive force between the negative end, partial negative end, I should say, on one molecule, and the partial positive end on the other molecule. And I can do that in a couple of different directions. These then are dipole-dipole forces. To turn that into real molecules that have our partial charges labeled out, at least on a couple, we can see that the partial charges are playing a role, and depending on how the things align themselves. Now, right now, these are all lined up nice and neatly. It wouldn't be like that in real life. They're always in constant random motion. These partial charges, these intermolecular forces, are going to be making and breaking all the time, but they're weak anyhow. So it's just an attractive force over here and now over there. Hydrogen bonding is the third type of intermolecular force, and the first thing I need to tell you about a hydrogen bond is that it is not a chemical bond. I didn't come up with the name, that's what it's called, but really important to understand is not a chemical bond. It's a strong intermolecular force of attraction, still weak compared to a chemical bond. Because it's so strong, it's going to have fairly strict criteria. And if you want a sort of a day-to-day life example, you can have a car, a regular car, and you can have a sports car. And all kinds of companies are making regular cars and sports cars. And sometimes it's just the regular car with two doors and maybe a little fin on it and extra little paint job to make it a sports car. But only a select few make supercars. And that's actually something very special. Bit of a lame analogy, I realize, but that's what we're talking about. Very strict criteria in order to become a hydrogen bond. Not that it goes any faster, though. Hydrogen bonds must have a hydrogen, figures, bonded to a fluorine, oxygen, or nitrogen. Now think about the periodic table for a second. Think about the trend in electronegativity. Those are up in that high electronegativity corner. And you must also have a fluorine, oxygen, or a nitrogen on a neighboring molecule. If you do not have that, you will not have a hydrogen bond. So, quick question here. Do those qualify? Well, I'm looking at this hydrogen to that oxygen. So I have a hydrogen bonded to an oxygen, and I have an oxygen nearby. Yes, it would. How about this one? Well, the way I've drawn this one, I'm kind of looking at this pair here. So I've got a hydrogen bonded to an oxygen, and I have a hydrogen bonded to a nitrogen. But no, because it's the nearby nitrogen isn't near enough, too far away, so no. Lastly, I've got a hydrogen bonded to a fluorine and an oxygen nearby. Yes, that one would work. A couple of questions to leave you with, some things to think about that we're going to deal with in class. Number one, so what? What does it matter that these things can have intermolecular forces? Okay, it said something about solubility and boiling points, but how much does it really matter? Second thing is, what if I have a lot of London forces? Sure, London forces are weak, but if I have a lot of them, does it then start to make a significant difference? And finally, what if I were to try and mix these things? If I have intermolecular forces between two molecules, what if I mix something that can do dipole-dipole with something that can only do London forces? What happens then? All right, back to Genius Day, April 1st, 1867. On that day, a man named Dr. James Lister performed the first surgery using antiseptic methods. In other words, he cleaned his surgical equipment. See, before that time, nobody thought to properly clean or sterilize surgical equipment, or even to properly clean the area around where they were going to do surgery. Sounds crazy to us, completely unreal, but the thing was, at that time, nobody knew about germs. The idea of something that was too small to see, but was still capable of causing great harm, they just hadn't thought about. So they never thought to sterilize equipment. They never thought to clean the wound or to clean the skin where they're about to do surgery. So thankfully, they learned a bit of chemistry, they learned a bit of biology, and society, as I said, has benefited greatly from it. We'll talk to you in class. Thanks for watching.